let me stop this. Yeah. If you can just go back to the beginning there. The remote controller doesn't work when someone's standing in between. Actually, you can just leave it there, and then if we can go over to these slides again. Yeah, the overhead. Next slide, please. Okay, the purpose of that was just to get us oriented a little bit. So early on, NASA, in fact, from the very beginning, Toby Owen noted face was dismissed as a trick of light and shadow, an optical illusion. So the question is it truly an optical illusion, or is it a real 3D object? It was hard to argue this early on because there were only 2 high-resolution frames, and they were both taken under similar lighting and viewing conditions. What you'd like is different lighting, different viewpoint. And if it looks like a face under all these different viewpoints, then you would conclude that it was probably intended to look like a face. It's not just a trick of the way it was lit from a certain direction or viewed from a certain direction. So the approach that I took was to reconstruct the shape of the face from the available imagery using a technique known as single image shape and shading. And I'll go into briefly ways of recovering the shape of a surface. This is the shape of the terrain from an image. Once we have this, then we can use computer graphics techniques to generate synthetic views. We can change the lighting, we can change the viewpoint. In a sense, what we're doing in the first part of that is doing inverse computer graphics. So instead of starting with a model and generating an image, we take an image and we try to figure out what the model is, the 3D model. Then once we have that, we can look at it in different ways. Next slide, please. So these are a couple different ways of recovering shape from images. One way is shadow analysis. You know, if you cast a shadow on illuminate an object from the side with a light source, it casts a shadow, and by tracing the silhouette, you can recover some of the shape information. But it's only limited. A more standard way of doing shape reconstruction is using stereoscopy. This is having 2 cameras set up a distance apart, and by measuring the parallax, the idea is that things that are closer have more parallax than things farther apart. You can map, by matching the 2 images, you can generate an elevation or a height map. Sort of like an image, but instead of the brightness being the reflectance, the brightness is related to the height or the depth of the object. Unfortunately, with the Viking data, both images were taken very close together, and you need images that are taken far apart, relatively far apart, for stereoscopy to work. So this left shape and shading, which was a technique that's was actually developed in the mid-60s in trying to map some of the lunar topography. A lot of work following that was then conducted at MIT, and then also in the planetary community is called photoclinometry. There's also a version that works for radar images called radar clinometry. Anyway, what you do is you start with a single image, and by making certain assumptions, you can recover the shape from that image. So if we can go on to the next slide. Basically, we assume an orthographic projection. In other words, the camera is fairly far apart from the image, or far apart from the scene, so you're not dealing with perspective distortions. And this is a good approximation for looking at the surface of a planet from orbit using a high-resolution camera. The other assumption is you're dealing with oblique illumination. In other words, the sun is off to the side, so you're getting good shadow and good relief. And we use a simple reflectance model called the Lambert model. And what this tells us, or helps us to do, is relate the brightness we get at a point to the slope of the surface. Portions of the surface that face the light source are brighter than portions that face away from the light source. And we use this cosine law where this angle here phi is the angle between the light source and the surface normal. This is the line that's perpendicular to the surface at that point. So as you can imagine, points that face the surface will be brighter than points that face away. The other element of the Lambert model is that the radiation is reflected uniformly in all directions. So the brightness only depends on the difference between the surface normal and the direction of the light source. Okay. Okay. Next slide, please. Now, with these approximations, we can come up with a very simple relationship between the image brightness and the slope. For relatively smooth surfaces under oblique illumination, the reflectance or the brightness is related, it's a linear function of the slope of the surface. And if we rotate the image so that the sun is, say, to the left or to the right or up or down, we'll pick to the left, then there's a relationship between the slope in the direction of the sun and the brightness in an even simpler way, shown here. What this allows us to do is to solve for the elevation, z, by inverting this equation, because really what this does is it gives us brightness as a function of z. What we want to do is get z as a function of brightness, so we turn it around and go through these steps. Next slide, please. And then we map it into a discrete, that is a computer form, where instead of dealing with a continuous function, we're dealing with a discrete approximation. If we assume that the surface or the object we're looking at, it has a uniform distribution of slopes. This would be true of any kind of smooth object, like a pebble or a face. And if we assume that the average elevation along all the lines is about the same, so it goes up by around the same amount that it goes down. And I won't get into the details of why this is, but what it allows us to do essentially is to compute surfaces that are smooth. And this is a computer network description of how that works. It's a very simple algorithm. And what this produces then is the elevation or the height of the object as a function of the brightness. If we could you turn this 90 degrees? Can you turn it 90 degrees? Could you flip it 180 so we get that on the bottom? Yeah, that's good. Great. They're all like that. Okay, this is the face in 7813, the top, and at the bottom, I don't know if you can see it, is a perspective view that's obtained by taking the elevation from the face and mapping it onto mapping the terrain onto that, sort of draping the original image over the height map and looking at it from the side. I have some video that'll go through this again. Next slide, please. This is a mosaic showing different views of the face taken from different rotations around it. The point of this is that the impression of a face persists for different viewing directions. And I'll have some other results that show that the impression persists for different light source directions as well. Next slide, please. This is the same result for this so-called D&M pyramid. Next slide, please. And for this object that I referred to earlier, the fortress. You can see it's an intriguing object. Appears to be a linear pattern here, a very straight side. These, from this angle, appear to be walls or if this was a solid object, part of it appears to have been stripped away. Okay, next one, please. Can you turn it? Turn it, flip it 90 degrees. 90 degrees. That's good. You can also perform this over larger portions of the terrain. You can create these landscape views. And this is the city and face taken in an oblique shot. And I think it shows some interesting, I think there's at least qualitatively an impression that you're dealing with more of a geometrical arrangements of objects there. Okay, I think that's the last slide on this. If we could run the video, please. Okay, I think this is the end of the last one. I apologize, it's a little distracting going back and forth between media. But we're almost there. In the next segment, we'll show the shape and shading results, some of the same things you saw in the slides. And I also have some images showing the face under different lighting conditions. Okay. So this is the process, again, that we're going through. We start with an image, we compute an elevation map. So dark means it's deep, bright means it's higher. Once we have that, we can compute a picture, a synthetic view of what that crater looks like under different lighting conditions. Okay, here, the top left, it's illuminated from this way. Here, we're illuminating it from the side. And in this pane here, we see the same crater, but now from a different view, looking at it obliquely. This is the face seen under different lighting conditions. We're varying the light azimuth, if you will, by about 45 degrees. And you see a change in the impression. I'm not drawing any conclusion from this. My only point is that the impression of a face is stable. It still looks like a face when we move the light source. The expressions change, which is interesting. This you saw earlier. This is the process for 7813. The original 7813 face upper left, the elevation map upper right. The lower left is what 7813 should look like given this model. In other words, we run the model backwards, and if we did a good job, we should get the same thing we started with, and they do match. But now we can change the light source position here and predict what it looks like in the AM. That is with the sun from the east rather than from the west. And this is a comparison of that predicted AM view with the only morning shot of the face that exists. This is 753A34 taken several years later, very, very, very low resolution. And it's very hard to make out anything. But there is, if you squint and you stare at it long enough, you can convince yourself that they match. And this you saw also. I think the other two things that are on this segment are some shots I did off the computer. Carl Sagan redid Cosmos a couple years back, and he asked for this segment. I don't know where he saw it originally, but he wanted to include it in the new version of Cosmos. Which I think is significant. It's showing at least some movement in the direction of maybe being a little bit more open. The other thing that we did several years back when I was at Task was we did a terrain animation, sort of like JPL did, Mars the movie. This is a portion of it, and you can see the city here moving past us to the left, and we'll go back and forth a few times. I'm not sure this provides a lot of new information, but it's pleasing to look at. Okay, we're about ready to stop the video. When you can go, yeah, stop it right there. Good. And if we could switch the slides then. Okay, I guess before going on to the fractal analysis, let me just conclude this part by saying the results of the shape and shading analysis, I think, show that the face on Mars looks like a face when you look at it from other perspectives and under different lighting conditions. Therefore, it can't be a trick of light and shadow. This has been published in a peer-reviewed journal, and it's certainly open to debate on the methodologies, but this is really a summary of the methodologies that I did use. And I guess the other point worth noting is that we do have some correspondence between the predicted morning view and this low resolution 753 A34 frame, but it's marginal at best. Okay, next slide, please.